Pascal's triangle, what number did you find for this first box? 5. And 5 over here. What about this one? 15 and 15. So let's talk about the 5. How many people found the number 5 because they were good at counting and went 1, 2, 3, 4, 5? You didn't even think about it, but that's kind of neat, eh? Some people did that, yes? How many people got 5 because they looked at the numbers above and said, ooh, 1 plus 4 is 5? Okay? Now, the 1 plus 4 is 5 works really nice for the 15, doesn't it? 5 plus 10 is 15. But did anybody do 1, this was plus 2, plus 3, plus 4, plus 5? Yes? Okay. This row of numbers, the 1, 3, 6, 10, 15, inside Pascal's triangle is a famous set of numbers called the triangle numbers. Because if you start making triangles with dots, pretend that's a triangle. But then add 2 dots on the bottom, that's the next triangle. Then add 3 dots on the bottom, that's the next triangle. And then add 4 dots on that's the next triangle. And they will add up to those numbers, the number of dots that you have. The triangle numbers also represent the arithmetic series 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9. Interesting. Okay. I'll tell you all interesting stuff that comes up, but let's get our next row. Did anybody realize that every row always started with 1? Yes. Good. Nobody used this strategy? 1 plus nothing is 1. It still works. Okay? And then we got 7. Add these two, 21, 35, 35, 21, 7, and 1. Nice. Now with Pascal's triangle, we're going to look right now at a bunch of patterns in Pascal's triangle. Eventually, we're going to lead towards how we're going to use Pascal's triangle and the next section of our notes called the binomial theorem. But first of all, one of the other questions I asked you is, where have you seen these numbers before in the questions that we're doing? In those pathway questions where you had to get from point A to point B. Right? You always added the previous 2 intersections to get to the next one, and these numbers appeared. Some other things. Okay, right now I'm just going to show you some really cool, interesting things about Pascal's triangle. So some people got the number 20 here by going 10 plus 10. And maybe someone figured out a pattern that you went up 3, up 6, up 10. I'm not sure. That would be a little bit harder pattern. But another way that you can figure out any number in Pascal's triangle, and in some places this is called the sock rule, but I like to call it the hockey stick rule because we're in Canada, is if you make a hockey stick, beautiful hockey stick, the numbers in the shaft of the stick, 1, 3, 6, 10, always add up to the number in the blade of the stick, as long as you're starting from the edge. And that works for any number. If you would go 1 plus 3 plus 6 plus 10 plus 15, you'd get 35. That's pretty weird. Now, some not so exciting things, but kind of neat. Did you notice that it's symmetrical? If you drew a line down the middle, the numbers on the left side are equal to the numbers on the right side. That's okay, I guess. It's not like a super exciting math pattern, but it's something to notice. Did any of you add up the numbers in the row? 1. There's 1. 1 plus 1 is 2. 1 plus 2 plus 1 is 4. Add the next row, 8. Add the next row, 16. What's the next row going to add up to? 32. What are those? Yeah, the proper math terminology that you're looking for is the powers of 2. Yes. Oh, yeah. That was close. Yes, the powers of 2. And that works, and that keeps working all the way through. Did anybody just think of them as numbers? This is the number 1. This is the number 11. This is the number 121. 1,331. Oh. Wow. Anybody think of those numbers? And then this would be 14,641. What's cool about those numbers? They're powers of 11. This is 11 to the 0. This is 11 1. This is 11 squared. And sure enough, this is 11 cubed. This is 11 to the 4. Isn't that crazy? And then there's an issue with 11 to the 5 because you don't have 10 ever in a digit spot. However, if you would work backwards and start with 1 and then a 5 and then 10, well, that would mean 0, add 1 to this one, 11, add 1 to this one, 6, 1. Sure enough, that's 11 to the 5. And that keeps working all the way through. That's a little crazy, eh? That's a little fancy. Who knows if he spent this much time looking at it or if all of these crazy things got discovered afterwards and then that made it famous, right? Sometimes you see a simple pattern, you look at that pattern makes connections to a bunch of other things, and then, wow, it becomes famous, right? So there's the powers of 2, the powers of 11. All right. Not done yet. Let's go with, I'm going to take a line. I'm going to draw this line as carefully as I can. That look good? How about there? Let's see, am I happy with that line? Maybe. There we go. Oh, that looks much better. How's that line look? Oh, I like that line way better. Okay, so let's take this line. Let us clone it. And if we take this line and drag it until we hit a number, we hit the number 1. We take it again and drag it until we hit the we hit the number 1. And if we do it again until we hit numbers, this time we hit a 1 and a 1. That makes 2. And next time we hit the number 1 and 2, which makes 3. And the next time we hit 1, 3, and 1, it makes 5. And the next time we hit, wow. And the next time we take that, we hit 1, 4, and 3, which makes 8. What are these numbers? Have you ever seen these numbers before? They're probably the most famous sequence of numbers that exists. They're the Fibonacci numbers. How many people have heard of the Fibonacci numbers besides Taryn? Yes? How do you find the next Fibonacci number? What is the next Fibonacci number? 13. Okay, if you already know how to find it, you can't answer the next one. What's the next one? 21. So if you already answered that one, you can't answer the next one. What's the next number? 34. How do you find the next number? Add the previous two. Why are the Fibonacci numbers so famous? I'm getting off topic. Are you okay with getting off topic about interesting numbers? Yes? Okay, so the Fibonacci numbers, why are they so famous? Where did they come from? Okay, the initial Fibonacci numbers came from hypothetical reproduction of bunny rabbits. That's okay. So this is how it started. Okay, and in this ideal bunny rabbit world, we are not concerned about any kind of incest or anything like that. Okay, there we go. Just, there's the preliminaries for this theoretical math question. You start off in the ideal bunny world with a pair of baby bunny rabbits. Cute. And you have a baby boy bunny rabbit and a baby girl bunny rabbit. So how many pairs of baby rabbits you have is one. You have no adult rabbits, and you have one pair of rabbits in total. Okay? I'm not sure what the actual lifespan of rabbits are, but let's say 1 week later they're adults. Do bunnies become adults in a week? Probably not. But let's imagine they do. In this ideal world, they do. So the next week, there's no more baby rabbits. They are now adult rabbits. And you still have a total of one pair of rabbits. Now, in this ideal rabbit world, every adult pair of rabbits has a baby pair of rabbits who happen to be a boy and a girl. So next week, these are still adults, but now you have a new set of baby rabbits. And you have 2 pairs of rabbits in total. What happens next week? Okay, oh, in this ideal world, bunnies never die. It is the ideal world, right? Okay, so the next week, this adult pair has another baby pair. This baby pair becomes an adult pair, and we have 3 pairs in total. The next week, the 2 adult pairs have 2 baby pairs. This baby becomes an adult, and you have 5. And the total is the Fibonacci numbers. Now, just because somebody thought about ideal bunny mating rituals, that doesn't make a set of numbers famous. But what makes the Fibonacci numbers famous is that after looking at them, they started to appear all over in nature, and we're going to see that they appear in, like, it appears in architecture, in music. And so, first of all, in nature, people started to notice that if you watch a plant grow, it comes out of the ground and it has 1 stem. Wow. Then it gets some water and it grows into a stronger stem. But once a stem gets stronger, the next time it branches off with a weak stem and a strong stem. And then the strong stem branches off again and the weak stem gets larger. This one now can branch off, and this one gets larger, and this one branches again. And if you do the cross sections of how the plant grows, 1, 1, then there was 2, then there was 3, then there's 5, and so on. And so it sort of creates a model for how a plant grows. But then there's the interesting thing about flowers, in that most flowers, the amount of petals that they have is a Fibonacci number. There's flowers that have 5 petals. There's flowers, groups of flowers that have 8 petals. Then there's not lots of flowers that have 9, 10, 11, 12, but there's groups of flowers that have 13 petals. And even if you would look at something like a sunflower has lots of seeds. And if you look at the sunflower, you can see a spiral of seeds in one direction. And if you look at it, you can also see spirals of seeds in the other direction. And if you count how many seeds are on the outside in one direction, you'll get a Fibonacci number. And if you count how many seeds are in the other direction, you'll get the next Fibonacci number. So it's really, really strange. And as you go up with your Fibonacci numbers, and you divide them, right? 2 divided by 1 is 2, 3 divided by 2 is 1.5, 1.6, 1.625, 13 divided by, no, that's 13 divided by 8. 21 divided by 13 is 1.615, and they start to approach this number. If you keep dividing them higher and higher and higher, they start to approach this number, which is known as the golden ratio. It's even given a Greek letter, phi, phi, 4, funny, I'm not sure which, phi, phi, phi. I think that's how you write it. Might be wrong. They give it a special number, 1 plus the square root of 5 over 2, because this number, this ratio, shows up everywhere. And so if you would take a rectangle, this is called the golden rectangle, by the way. I don't know if it's perfectly drawn, and it's in black. I should have used a gold pen. The golden rectangle has that if I take this side and divide by this side, I get this number. 1 plus the square root of 5 divided by 2. If you want that as a decimal, I'll write it for you right now. .618 ... Now, interesting thing about this rectangle is they've done surveys. They draw a bunch of different shapes and ask people what shape they like the best. And predominantly, people will choose this shape. Why would you choose a rectangle? Okay? And interestingly, you don't realize this, but this shape has been used in your life to, for marketing purposes, right? The shape of your credit card. It's like, ooh, I like this. I should spend money. I should spend money. Cereal boxes and drink boxes are in shapes that you go, I like this. The Greek ancient, in ancient architecture, the ancient Greek Parthenon, they've done measurements, and it was built on this rectangle. Now, did they know the rectangle first and build it? Or did the architects just say, I want to build the most beautiful building I can imagine, and this is what I came up with? Is there a relationship between that and the number? And then, you know, the golden ratio proportions, your body is built on the golden ratio. If you measure how tall you are and you measure how high where your belly button is, the ratio of your height to your belly button is really close to 1.618. The golden proportion. If you meet someone whose belly button is up here, right? You'd be like, that person is disproportionate because they don't fit the golden proportion. Your ratio between each of the joints in your fingers. If you divide that length by that length, you get close to the 1.6. That length divided by that length, close to the 1.6. Right? And so we have these ideas of proportions, and they all fit with this rabbit reproducing world. And the most typical cover on a math textbook that has ever existed, if you would like study all math textbooks ever, you will find that the Fibonacci numbers appear more often than anything else. So here's the current IB textbook. It's got some sort of plant that spirals because of the Fibonacci numbers. Here's another textbook. Probably the most famous picture is of a snail on a math textbook. Because if you were to take your Fibonacci numbers and you would draw a square that's 1 by 1 and add another square that's 1 by 1, and then you could draw a 2 by 2 square, and then a 3 by 3 square, and then a 5 by 5 square. If you start in the corners of your square, that is the curvature of a snail. So kind of crazy. And then musicians have taken the Fibonacci numbers. Like a famous symphony by Beethoven, Beethoven's Ninth. You've probably heard it before. It's that one that goes ba-ba-ba-bum, ba-ba-ba-bum, and it keeps going and on and on and on. So I'm not sure the exact number. I might be wrong here, but if I write a couple more, we've got next number is going to be 144, and then after that 233, and then 377. So Beethoven introduces his theme in bar 1 of measure 1 of his symphony. He then goes 233 measures before he reintroduces the theme again for the second time. So he introduces the theme once, and then he plays around with it for 233 measures, and then reintroduces the theme and takes another 144 measures to finish the song. Did he know about these numbers and do that on purpose? Or in his mind, did that proportion sound the best? Did it sound the best to have this length of music and then finish off with another length of music? Interesting stuff. All of this, sorry, Fibonacci numbers, I was getting a little bit off track with Pascal's triangle, but Pascal's triangle connects to the Fibonacci numbers. There's other cool connections. In Pascal's triangle, if you were to shade all the even numbers, all the way through and make it bigger and bigger and bigger, it makes Sierpinski's gasket.
What
No, sorry, that's not Sierpinski's gasket. It's Sierpinski's triangle. Sierpinski's gasket is a bigger thing. Sorry.
Why would you just think like, I want that to be called my gas?
So, I'll show you a picture. Oh, I'm sorry. I'm getting way off topic today. All right, let's go. What color would you like to see Sierpinski's triangle in? Okay. Or I think I have just a second here. I think I have. Let's see. There, we can pick. We'll do a fast version in what color? 7. Okay, so first of all, what is going to happen here is this program picks a random spot on the screen. There's going to be 3 dots in that represent the corners of an equilateral triangle. It then randomly picks one of the corners, and wherever it is, the dot moves half the distance to that corner and draws another dot. Then it randomly picks another corner and goes half the distance to that one. So the whole thing is random all the way through. And this is what happens. We'll start with green. Okay? It was a fast version. Okay? So I can tell that the first dot that was chosen was right here. This was the first random dot. Then it picked this corner up here and moved half the way to there. Then it picked this corner and moved halfway there. Then it picked this corner, moved halfway there. Back to this one, halfway there. The thing is once it gets into this pattern, it can't get out. Can you see that once it gets inside the triangle, it never gets out of the triangle again? And no matter where you start with randomly picking a point, where you start with randomly picking a point, you always end up with this shape, which is kind of weird. Let's go yellow. Oh. It always creates the same thing. And if you were to make a huge Pascal's triangle and black out all the even numbers, you would get Sierpinski's triangle. Now, this kind of mathematics, they're saying perhaps this is how some of genetics work, because there's not a lot of information you can hold in genetics. You have a little bit of information, and yet I've yet to see someone plant a watermelon seed and up sprouts a monkey, right? That hasn't happened yet, right? Just wait, right? How is it that a watermelon seed always makes a watermelon, an apple seed always makes an apple, and no apple tree looks the same, but they all look similar? Well, maybe it has something to do with this pattern that they notice mathematically. There is a code built in, a rule built in, that it just needs to repeat itself. And if it repeats itself, it always creates the same shape, more or less in the end, just a little bit different here and there. Okay. So, why are we doing Pascal's triangle? Where does it help us? How does it fit into combinations? Well, if we would look at this row here, just randomly, and I think this might even be on the next page, but we'll go to it after. I have 1 happens to be equal to 3 choose 0. 3 happens to be equal to 3 choose 1. 3 is equal to 3 choose 2, and 1 is equal to 3 choose 3. Later on in your notes, they say, look at these ones. 4 choose 0, 4 choose 1, 4 choose 2, 4 choose 3, 4 choose 4. Well, this is 1, 4, 6, 4, 1. Oh. Way to ruin a good class, Mr. JR. Bring combinations back. And so all of Pascal's triangle can be represented with combinations. And so on and so on. And what the area that we're going to use Pascal's triangle for and the combinations for is when expanding binomials. So what does that mean? Well, to introduce it, if I had x plus y to the 0, what's anything to the 0? 1. Good. If I had x plus y to the 1, I would just get x plus y. In fact, I would get 1x and 1y. If we did x plus y squared, you'd FOIL that out, right? X plus y squared, you'd FOIL it out, combine your like terms, you'd find out that you get x squared plus 2xy plus y squared. Oh, you happen to have 1y squared, 1x squared, and 2xy's. What do you think happens if you took and did x plus y cubed? Well, you'd have to FOIL 2 of them and get x squared plus xy plus y squared, and then multiply by another x plus y. This could take some time. Combine all your like terms, and you get x cubed plus 3x squared y plus 3xy squared plus y cubed. And if we did one more, and then think about this last one, we would get x to the 4. I want to see if you can see some patterns here in the variables as well. So I hope my color coding has helped you see something. The coefficients are just from Pascal's triangle. The variables, can you see that you start with x to the 4, and then you have 1 less, you have x cubed, and then x squared, then x, and then no x's? Now the question is, how is this, right? This is 4 choose 1. How is 4 choose 1 related to multiplying out x plus y to the 4? This is what x plus y to the 4 means when it's expanded. X plus y times x plus y times x plus y times x plus y. Okay? And if we made some sort of acronym for all the things that get multiplied, one of the things that gets multiplied is all of your first terms get multiplied together. That gives you your x to the 4. When all of your last ones get multiplied together, that would give your y to the 4. But then you have to do some outside, inside, inside, outside, outside, inside ones, and outside, inside, outside, outside. Like so many different combinations that if we made an acronym for this one, it would be like which would be hard to remember if you did all the oys and the oys in between. But this 4 choose 1, if you were going to multiply all the different arrows that are possible, and you wanted to get 1y, and every time you multiply, you take one thing from the first and multiply by one thing in the second, and multiply by one thing in the third, multiply by one thing in the fourth. And I want to get 1y. How many y's are there? There's 4 of them. And I need to choose one of them. How many ways can that be done? 4 choose 1. So there's going to be 4 times that a y gets multiplied with 3 x's. If you wanted 2 y's, this number right here is 4 choose 2, because it doesn't make a different term if I change the order, but getting 2 y's no matter which order there are, how many different pairs of 2 y's could I have? I could have this y and this y, 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 this y, this y. There'd be 6 different ways you could choose 2 of the y's, and then the other ones would have to be x's. And so when it all gets multiplied out, that's why there's 6 x squareds, y squareds. So that's the connection between multiplying out and combinations and Pascal's triangle. So what we're going to do next is we are going to turn to section 8.6. And in 8.6, it looks at the binomial theorem. It says, what row is this? How would you know? It does some expansions, and it shows exactly what we saw before when we expanded things. So we look at some patterns. If you had to do x plus y to the 6, well, you could go to Pascal's triangle and find the numbers that would go out in front. So some important things to notice. That if your power is a 6, there are 7 terms. And one of the ways that I remember this special pattern is I just think about something I know I can expand easily. If the power is 2, what's x plus y squared? X squared plus 2xy plus y squared. That's one you can foil in your head. How many terms are there? 3. There's always one more term than whatever the exponent is when it's expanded. So if we look at example 1, I'll stop this video here.